question. How fun was that quiz? It was decent. We'll find out, eh? You'll find out pretty soon how you did once I show you the next slide. So, question though, seriously. We've talked about ionic compounds, yes? True? Metals, look over there, metals, nonmetals, yes? So metals and nonmetals. We've talked about molecular compounds, nonmetal, nonmetal, yes? What does that leave? Is there anything to do with just metals? So is there some type of bonding that is just for metals? Metals and metals, for example. Can metals and metals combine together? You betcha. Okay? So we've done metals and nonmetals. We've done nonmetal, nonmetal. Today we're going to do metal and metal. In fact, I took you guys to the lab the other day, well, a while ago. I hope you enjoyed it. That was the only lab you get to do this year. I'm just kidding. Psych. That's an old term. You're too young. All right. Anyway, for example, right? Think about this. I showed you guys lithium, sodium, and potassium. Remember those sticks? And I cut them and I put them into water. Yes. Remember, if you look over there, first of all, they're in solid form, et cetera, et cetera. But let me ask you a question. Can you see think back to the last one, the very reactive one, potassium. Can you see a potassium atom? Can you see a potassium atom? Yes or no? With your naked eye? No. Can you see 100 potassium atoms? No. Can you see 1,000,000 potassium atoms? Can you see this is a made-up number, so don't hold me to it. Can you see a kajillion potassium atoms? No. Because they have to be, you can't see individual atoms. They have to be bonded to each other in some way, shape, or form. So that's what we're going to do today. It's called, believe it or not, metallic bonding. Ooh. So, you know that chunk I had? There was literally probably a babillion potassium atom, that's a made-up number, babillion potassium atoms all joined together somehow. How? Metallic bonding. What's metallic bonding? Well, thanks for asking. I'll tell you. First of all, before we get there, right, if we're doing ionic compounds, we show metal, non-metal, we show electrons moving, yes? We show that. Opposites attract. Everyone's like, some people are like, other people are like, oh. Hey, those are the people that will work, all right? We'll work on it. We got molecular, yes? Sharing. What about metal? Just metals. Okay, so metal, non-metal, non-metal, non-metals. What about metal and maybe another metal atom together? How are we going to show that? What does that look like? Okay, and that's what we're going to do today. So, in fact, you can combine metals together. In fact, not only can you combine sodium atoms together, you could actually combine numerous metals together. So, for example, when we talk about alloys, yes, you guys have heard alloys, right? Alloy rims on your car, magnesium and aluminum together forever. Yes. Or bicycle frames or motorbike frames or whatever. You combine different metals together to give them slightly different properties. That's metallic bonding. Okay. Now, you might say, how do I do metallic bond? Do I take a chunk of metal and another chunk of metal and I put them together? Well, no, because they're not going to mix. You usually have to melt them down and then let them re-solidify basically into a new chunk of metal. Depending on how much of each metal there is, gives it different properties. Okay, that's a little far for us yet. How does this happen though? How does that sodium chunk that I took, how is that all sodiums? How are they all bonded together? So that's what we're doing today here. Metallic bonding. You guys got a few notes here, so I'll pause it here for you, and you guys can write. Okay, so like I said, we talked about this already, but the one we're going to focus on today is metallic bonding. Once again, most of the metals at room temperature are solids, except mercury, but all the other ones are solids. That means that they have to have a strong enough bond to each other, strong enough force to keep them together very well, to keep them into a solid format or solid state. All right? If there was no forces, if there was no metallic bonding, gases very well, or sorry, metals could very well be gases. And of course, that'd be a little bit of an issue for us because you'd probably wouldn't have a chair to sit in and whatnot. The one important thing here is the bonds that hold metal atoms together are not ionic, and they are most certainly not covalent. Okay? They're not ionic and not covalent. It's a different type. Once again here, you have a few notes to copy, so I'll let you guys do that. We'll continue here. In metallic bonding, this is going to sound wordy. This is going to sound very, in some cases you might be like, geez, that's a lot of big words there. I don't know. It's fine. I'll draw you a diagram. Hopefully it'll make it a little simpler for you. But in metallic bonding, all the atoms are attracted to all the valence electrons. So the valence electrons are delocalized. They're kind of let loose, I guess you could say. So they are free to move from one atom to the next. You can visualize metallic bonding as a network of positive ions and a sea of electrons. The electrostatic attractive force, that's a fancy word for saying opposites attract, okay, between positively charged metal ions and electrons, okay, constitutes a metallic bond. Everyone got that one? Okay, so what does this look like? Well, we can pick yeah, oh yeah, positives, negatives, yeah. We can do any metal we want, basically. Some are easier than others. So we're going to stick to, you guys have a specific example already in your notes, but we're going to stick to like sodium, for example. Sodium, okay, there's its nucleus. I'm going to kind of draw none of the diagrams that we've talked about. I'm just going to draw the one valence electron just to kind of keep it simple. So here's sodium. Sodium has one valence electron, yes? 11 protons, 11 electrons, yes? 2, 8, and 1. So here's that 1, okay? Because really, ultimately, remember that valence electrons are kind of the most important thing for the most part, because they're what constitutes bonds, etc., etc. So here's another sodium with its electron, and here's another one with its electron. And I'm going to put one here with its electron. And I'll put one here with its electron. And one more. I'm not going to get too crazy here. Okay? So these are all sodium atoms. All right? They're just neutral right now, sodium atoms. These all represent their valence electron. Okay? So what happens with metals when a bunch of metals get together like this? Metals don't want to attract electrons, right? They want to lose them to become more stable. Sodium forms a 1+ ion, yes? Why? Because it loses that electron, becomes more stable, has a full outside shell. Well, that's what happens here. Now, normally we'd say, oh, sodium has to lose an electron. Where does that electron go? It goes to a non-metal, and it gains it. Well, with metals, they're allowed to lose that electron or let it go, delocalize it. So when we talk about local, this is your local community here, okay? That electron, this electron belongs to sodium here. That electron is going to be delocalized, so it doesn't necessarily belong to that community or that atom anymore. It's free to kind of go. So we get sodium, right? And here's that electron, and it's free to go now. You might say, what's the difference? Well, it's maybe just a little bit further away. But remember, that electron goes around and around. Maybe it's going around more than one atom now. Maybe it's going a little bit farther. But that electron's free. It's let go. So if sodium loses an electron, this becomes positive, right? sodium ion loses an electron. Where does that electron go? Not very far, probably. Still kind of around there. Might even still, in some cases, orbit around that particular sodium. Maybe it starts orbiting around a different one, or maybe it's just free to be let go. The same thing happens with this one here, okay, and another one here. Now you might say once again, what's the big difference between these ones and these ones here? Well, the difference is, which is a little hard to show you, okay, but the difference is that outside electron is free. It's free to go, and I'll show you the big difference here shortly. So here's my other one here, here's my other one here, and here's my other one here. Now I kind of drew these with a lot of space in between them, but I'll kind of, once again, I'll show you on the next page as well here, so just give me a sec. So these all become positive ions because they've let that outside electron go. They've delocalized that electron. What you now get is, the question becomes, is this attracted to this one here? Are those two attracted to each other still? Does that sodium, does that plus attract that negative electron? What do you think? Opposites attract. What do you think? Yes? No? Yes. But this is positive ion. It also likes that electron as well. So now what's happened is a different ion is free to be attracted to that electron as well, because that electron doesn't solely belong to that sodium anymore. It's free to be attracted by many different ions. Okay? And there's that one there and that one there. And this one here. Now there's not another one over there, but remember, I only drew 6 ions here. What if you had 6 billion, right? 6 kajillion. There'd be a lot of these attractions. And I'll show you on the next page here. This one's probably attracted to this one as well. Okay? Any electron that's close enough to it, you're going to get these attractions. Okay? Now, yes, I'm drawing lines. These are not covalent bonds. I'm just showing you that these two are attracted to each other. That is it. Okay? So, does this one attract to that one? Well, it depends on how close it is, but sure. These two are attracted to each other. That might be attracted to it, that might be attracted to it, and that might be attracted to it there. Oh, what about this one here? Sure. Why not? I don't know. Which one did I miss? This one? Oh, yeah, right there. So there's an attraction there as well. So what happens is they kind of all help each other out. First of all, what happens is they let go of their outside electron, or electrons in some cases. If you think about magnesium, it's got 2 valence electrons. It lets those 2 go. And what they do is they help each other out. They start becoming this positive-negative attraction. And that's what metallic bonding is. All right? That's what constitutes a bond. The definition of metallic bonding is this: positive ions in a sea of electrons. Think about, you're in a boat on a lake. Okay? You're the positive ion. The water is a bunch of electrons. Are you going to have a lot of attractions? Sure you are. Okay? Picture 500 boats in a big lake. More attractions, yes? Lots of attractions. Picture a kajillion boats on a really big lake. Sure, on the Pacific Ocean. You're going to have a lot of attractions. Okay? A lot of plus-minus stuff. That's kind of what this is. It's positive ions that are kind of embedded in the sea of electrons. And there's millions and billions and kajillions of positive ion electron attraction. And it holds together very well. Which one's stronger? Which one's stronger? Ionic compounds, opposites attract, or metallic elements, opposites attract? Somebody say ionic. Ionic. You're both right. It's a trick question. They can be equally as strong. Okay? Now, some are stronger. So we have some stronger metallic elements, and we have some stronger ionic compounds. Good thing for you, stick around. Last unit, I'll give you a little graph. It's very nice, and you'll see that. Okay. So metallic and ionic are very, very strong. Opposites attract. Molecular, sharing, weak. Weak. You're weak. Okay. All right, that's not funny. I was going for the Terminator thing there, but all right. Anyway, weak. All right. Okay. So opposites attract. Okay. So once again, you can visualize metallic bonding as a network of positive ions. We often use that term, network, because look, when you network, you have lots of conversations with other people, right? You have lots of, hey, this, how, right? You're all over the place. So you got lots of stuff going on here. There's lots of attractions, right, when you're networking, all right? Here's an example that I've given you with magnesium ions. Okay, each one of these magnesium atoms has let go of its 2 electrons. That's why you see a big 2+ for each one of these. Yes, because magnesium forms a 2+. And those now electrons that it's let go of, okay, are free to be attracted by any other ion that's around it. So at this current juncture, remember they're moving, but at this current time we got an attraction here. We got one there, one there, one there, one there, probably one there, one there, one there, one there. You don't have to do this. There's one there, there's one in behind there. Probably close enough, I would say, roughly. So you can kind of, oops, that's not even one there. But you got the idea, right? Look. And I'm going to stop because I'm getting tired. But you can see how many actual opposite attractions there are. And that's only with 2 rows. And there's what, 2, 4, 6, 8-ish or so, 9 there, right? Picture a babillion of these. And not only that, but picture them, sure, you think about this, but what about coming out towards you, 3-dimensionally? So if we stack another one on top of here, how many more attractions are we going to get? Exponentially more. What about, I don't know if that's true or not, but what about behind? What if we start making cubes out of these things, right? Really big things, 3-dimensional shapes. There's going to be, for every kajillion ions that you have, magnesium atoms that you have, you're going to have a kajillion times more, times kajillion, I don't know, I'm making stuff up. You're going to have that many attractions. You're going to have tons of attractions, all right? So it becomes very, very strong. And when they become very, very strong like that, that's why we have metals in solid form. That's why, although a little bit different, that's why ionic compounds are in solid form. Opposites attract, okay? By the way, we missed something here somewhere. Maybe it's on the next page here. The diagram represents magnesium atoms that have released their electrons that are embedded in a sea of electrons. Where did I live? I had it somewhere here. Maybe it's on this page. Oh, I did have it there. Must have erased it. So I will do one more thing for you. Yeah. Not necessarily. There's many, many, many factors that factor into that. So that's a good assumption, but not necessarily true. Yeah. 2 metals can join together like this as well. But you usually have to, like I said, if you just take a solid chunk of aluminum and a solid chunk of magnesium and you put them beside each other, you try to smash them, and nothing's going to happen. So, no. You do have to melt them to help them get those, to basically get them so that their electrons are free. In solid form, okay, you're not going to get that. But if you melt them down and mix them together, which usually takes a lot of temperature, depending on the metals, if you melt them down, that gives them that ability to start sharing and mixing. Exactly. What's a suit made out of? I am Iron Man. Maybe it's made out of iron. Except it would rust. Think about it. True. Yeah, it's true. Unless he's got cathodic protection. I know. I know it did. You'll learn about prevention of rust in Chemistry 30, so stick around. I am Iron Man. Oh, we're not done. Ionic, okay? So, you can write this wherever. I don't care where you write this. I'm going to simplify this for you. Ionic is based on opposites attract. Guess what? Leave yourself a little bit of room here. If you want to simplify the differences and the similarities between ionic and metallic, it's quite straightforward. Ionic and metallic is based on opposites attract. The difference wherein lies, this is a metal and a non-metal, of course, which you guys already know. Opposites attract, right? Based on sodium giving its electron to chlorine, becoming chloride, sodium chloride, metal, non-metal. Metallic is based on a metal and delocalized electrons. That's my abbreviation for electrons, E with a minus, comma S, electrons. Okay? If you want to write out electrons so you know what that is, feel free. Metal and delocalized electrons, that's how they're different. Okay? It's the electrons that the metal has lost. That's not sure, I shouldn't say lost, but let go of. Okay? So once again, going back to here for a sec, I'll come back to that if you want. But look, positive ions around a whole bunch of electrons, right? A sea of electrons. That's metallic bonding. I wasn't aware we're done. Hey? Are we done? I didn't realize that.